we've made sense of how to give a value to a series, and we've also seen an example that leads us to believe that actually finding the value of a series is very difficult in general. But there is a certain kind of series where finding a value for the series is doable. And this seems like just a stupid math trick that would never actually come up in practice. But in fact, it does come up in practice. So let's have a look. Let's see if we can figure out a value for this series. We'll figure out if it converges, and if so, what it converges to. So the sum from n equals 1 to infinity of minus 1 over n squared plus n, maybe it seems implausible that we would be able to find a value for this. But there's a trick. There's a trick hiding, which is, right, one thing that you might try is, like, this is a rational expression in n, and its denominator factors, right? Hopefully you notice that. And now that the denominator is factored, remember, if you have a rational expression with the denominator factored and the numerator has a lower degree than the denominator, you can do partial fractions. It's hard to know ahead of time if this helps, right? It's not at all obvious that this would help, but let's try it. So I'll let you work through the algebra of the partial fractions. What you get is 1 over n plus 1 minus 1 over n. Okay. To check that this is correct, you could take this expression and just put it over a common denominator. And if you do that, it simplifies back down to this. Okay. So just to understand what's going on here, let's write out the first few terms of this series. So let's see. When n is 1, we're going to get 1 over 1 plus 1 is 2 minus 1 over 1. So that's the n equals 1 term. And then plus, let's write out the n equals 2 term. That's going to be 1 over, let's see, 2 plus 1 is 3 minus 1 over 2 is 1/2. Good. Plus, and then the n equals 3 term is going to be, well, it's going to be 1 over 3 plus 1 is 4 minus 1 over 3, and so on. But wait a second. You can see that there's a lot of canceling that's happening here, right? So this is going to cancel that. This 1/3 is going to cancel that 1/3. And then, I mean, in principle, there's a 1 over 4 hiding in here, and that's going to cancel this one. So this series, it's actually collapsing down a lot, right? Part of one term is canceling with part of a later term. And since this is sort of collapsing down, it gets called a telescoping series, like one of those old-timey telescopes that kind of goes out like that. Because when you collapse those, right, one piece slides into another and the whole thing gets smaller. Well, that's what's happening with this series. So that's the intuitive idea, but we need to be a little bit careful to make sure we don't make any mistakes about what is happening with this series. When I say be a little bit careful, what I mean is let's actually write down what is the nth partial sum and make sure that we know what happens to the limit of the nth partial sum. So the nth partial sum is, let's see, it's going to be 1/2 minus 1 over 1 plus 1/3 minus 1/2 plus, and so on, down to the nth term. And the nth term is going to be 1 over n plus 1 minus 1 over n. Okay, and now let's see in this partial sum what cancels. So this 1/2 cancels that minus 1/2. There's a plus 1/3 here, and there's a minus 1/3 hiding in here, right? So those cancel, and so on, all the way down to, well, in the term before the one that in the term before the last one, there's a plus 1 over n, and so that's going to cancel this minus 1 over n. So everything cancels except the terms at the end. So we have a minus 1 plus 1 over n plus 1. Okay, so now that we know what the nth partial sum is, we can take a limit of this nth partial sum, minus 1 plus 1 over n plus 1. And, well, in the limit, this 1 over n plus 1 is going to go to 0, of course, and so we're just left with minus 1. So the value of this series is -1. This series converges to -1. And that's seems a little crazy at first, because if you write out what the terms of this series are, right, when n is 1, you get -1/2. When n is 2, you get minus, let's see, 4, so 1/6, and then minus, let's see, 9 plus 3, 12, and, right, so this, if you just look at this and somebody told you, hey, this is -1, it seems implausible, but it must be true. I mean, we just proved it, right? So it must be true. And we use this idea of writing out the partial sum, collapsing the partial sum like a old-timey telescope, and then seeing what happens to the result. Okay, let's do one more example like this. So let's look at the series, the sum from n equals 0 to infinity of the square root of n plus 1 minus the square root of n. Does it converge, and if so, to what? Now, because of the n plus 1 here and the n there, right, the temptation is to say, well, look, the same thing is going to happen. When we're starting at 0 this time, so we're going to get 1 minus the square root of 0. That's the n equals 0 term. And then the next one is going to be the square root of 2 minus the square root of 1, and so on. And right, this is going to cancel this, and this is going to cancel the next one along. And so everything's going to cancel. Well, sorry, this doesn't cancel, but it's 0. Everything is going to cancel, so we just get 0. So the temptation is to say that this is 0. But let's be a little more careful. Remember, to be careful about finding the value of a series, we need to write down what the partial sums are. So let's see. So the n equals 0 term is the square root of 1 minus the square root of 0 plus, and then the n equals 1 term is the square root of 2 minus the square root of 1, and then so on, down to the nth term is going to be the square root of n plus 1 minus the square root of n. Okay, this square root of 1 cancels that minus square root of 1. This square root of 2 cancels the minus square root of 2 that will show up in the next term, and so on. In the term right before the last term, there's a plus square root of n, so that cancels this one. And so the nth partial sum is, let's see, this 0 survived, but 0 is 0, so let's not write it down. And then this square root of n plus 1 survived. Okay, so this is our nth partial sum. And now we can take the limit as n goes to infinity of our nth partial sum. So this is the limit as n goes to infinity of the square root of n plus 1, but this limit is infinity, right? So this series, this actually diverges to infinity, right? So you can see that it is dangerous to jump to conclusions with telescoping series, right? If you don't think about it carefully, if you use this intuitive way of thinking about it, you might talk yourself into thinking that this is 0, that this converges to 0. But in fact, this series diverges. So, right, you got to be careful with series. Right? Got to be careful with series. In particular, with telescoping series, you really do need to work out what the partial sums are, so you know what happens to this last dangling uncanceled bit.